So the next speaker is Yuanfei Xiao from Yunnan University, and his title of the presentation is Cost-Efficient and Reliable SFC Orchestration in Mobile Edge Computing. So here is his short bio. So Yuanfei Xiao is a graduate student at School of Software, Yunnan University. His research interests include network function virtualization and edge computing. In his presentation, he will introduce A2C SFC, a two-stage deep reinforcement learning framework for cost-efficient and reliable service function chain orchestration in mobile edge computing.
Good afternoon, everyone. I'm Yuanfei from Yunnan University. Today, I'm honored to present our work titled Cost-Efficient and Reliable SFC Orchestration in Mobile Edge Computing. Next, I will introduce our work in the following 6 chapters. The first is background and motivation. The convergence of network function virtualization and mobile edge computing enables flexible, low latency service delivery in applications like smart cities and industrial Internet of Things. To enable such services, several functions are developed to process data through a sequence of virtual network functions. However, orchestrating SFCs in edge environment is particularly challenging. We need to simultaneously optimize latency, reliability, and cost, which often conflict with each other. Let me summarize the core problem. EMEC SFC orchestration requires joint optimization of latency, reliability, and cost, but those objectives are tightly coupled. Optimizing them independently leads to suboptimal solution. Existing dependencies are most static and inflexible, unable to adapt to dynamic workloads. And a unified and scalable framework is still lucky. Existing methods typically optimize only a single objective or a subset of goals, eliminating the full trade-off and interdependencies among all three. To solve those key changes, we first introduce our system model and formulate the optimization problem. Our system model is as follows. The MEC infrastructure is modeled as an undirected graph. Each node presents an edge server with limited memory, CPU, and value weight and cost, and each link with associated bandwidth and propagation latency and cost. Each SFC is a sequence of virtual network functions with constraints on delay, reliability, and resource demand. And the end-to-end delay consists of transmission, propagation, computation, and initialization latency. The SFC reliability is composed of physical node reliability and VNF reliability, and the total deployment cost consists of 3 parts: computing and memory cost for VNF execution, band cost for VNF data transfer, and redundancy cost for reliability assurance. And our optimization goal is to minimize the total cost while satisfying delay and reliability constraints. To solve this, we propose A2C SFC, a two-stage deep reinforcement learning framework. In stage 1, we use an Advantage Actor-Critic agent to place VFS across edge nodes, and then solve a KT-based resource allocation problem to distributed CPU. In stage 2, we apply a lightweight heuristic algorithms to deploy redundant VFS on distant nodes in order to satisfy reliability constraints at minimal cost. In stage 1, SFC placement problem is formulated as a Markov decision process. The stage includes the current SFC request and the MEC environment, and the action is the decision to location of each VF. The reward is the negative cost. After placement, we use KT condition to solve the optimal CPU allocation, minimizing compute cost on the delay bounds. In stage 2, we identify the most vulnerable VFS based on the both node and the function value probability. We then deploy back instances on appropriate physical node. The goal is to continuously select VFS for backup and choose appropriate placement locations for redundancy until SFC reliability meets the requirements. When choosing where to place the backup VF, we consider the following factors. Backup must reside on a different server than primary instance, and located within a hop distance from both primary and adjacent VFS, and must meet the memory requirements. We pick the lowest options, starting with nearby nodes and expanding only when necessary. This strategy ensures the overall SFC reliability exceeds the given threshold, while minimizing the redundancy overhead. In evaluation stage, we simulate a 20-node physical network where each link has a 30% probability. And there are 50 VNF types, and each SFC consists of 3 to 6 VNFs. We compared each SFC with GIPS, PPO, and greedy algorithm across metrics like cost, initialization time, and execution time. The following are cost parameters for a fixed number of SFC requests of 5, 10, 50, and 20 per 10 slots. A fluctuating number of SFC requests between 10 and 20, and a cost parameter of different reliability deployment stages. It proves that each stage of our two-stage agreement has a good effect in reducing cost expenditure. And next, we show the convergence performance and execution time comparison of our agreements. Experimental results show that our agreement has a good robustness and can achieve millisecond level decision making. To summarize, we propose A2C SFC, a scalable two-stage deep reinforcement learning framework for cost-efficient and reliable SFC orchestration in MEC. Our method integrates A2C placement, KKT-based CPU allocation, and heuristic redundancy. Experiments show significant improvement in cost delay and reliability on the dynamic traffic. In the future work, we plan to add VNF workload prediction and scaling stress, and support reactive fault recovery, and validate our method in real-world MEC deployment, evaluate it practically and scalability in production environment. Thank you for listening, and I'm happy to take questions now.
Okay, so I have a question for your modeling part. So can you go to page, let's see, page 5? So the modeling, so going, yeah. Yes, so yeah, here. So I'm wondering for your, oh, sorry, not the one, the VF modeling, maybe going later. So there's a slide. Let me see the slide. Yeah, the very next one, the six, the very next. Yes. So I'm wondering if given a new network function, right? So how you do the modeling by hand, or like, for example, you have a computing and memory cost, how you mark the computing and memory cost of a new network function?
The server provider will rent a resource to provide the SFC survives. Mm-hmm. And the rental cost is decided by the rental duration, yes, and the rental size.
Yes.
And the rental price.
Yes, so then maybe it depends on how like, for example, if since this might run on CPU, right? So then the total amount of traffic it processes will change the computing and memory consumption, right? For example, if you produce very small flows, then you don't need a lot of CPU, right? But if you have a large volume of traffic, it might cost you a lot more CPU. So how are you going to balance the two cases?
The memory is decided by the data size needed to be processed, and the CPU is allocated by the latency constraints and allocated by the KKT condition. I see. We can get the optimal CPU allocation and maintain the latency constraints.
I see. Okay, great talk. Thank you.
Thank you.